Hey, Wheaton North, Mr. Yergler here. We're going to talk about using energy transfer to identify unknown metals. All right, let's get started. We've already talked about calorimetry a little bit and how energy transfers from hot objects to cold objects. So if you take a look at this picture up here, we have hot water and it's transferring its energy to cold water through that metal barrier or that metal plate. Now, eventually, their two will end up at the same temperature. That would be called thermal equilibrium or just equilibrium. Energy is always transferred from hot objects to cold objects because the molecules are always bumping into each other and transferring that energy. Now, the metal's energy can't be measured directly. We can't directly measure how much energy is being transferred. There's no tool that measures that. But what we can measure is the temperature change. So we're starting here at 90 degrees and 10 degrees, respectively, for the hot and cold water. Eventually, they're going to come to the same temperature, right? Equilibrium. That temperature is going to be probably somewhere around 50 degrees, the average between the two, assuming that we have the same amount of water on both sides. Now, we can easily measure that temperature change with a thermometer, right? Water has gone from 90 to 50, and cold water has gone from 10 up to 50, right? They actually have equal temperature changes in this case because we have equal amounts of the same substance. A calorimeter is simply a device that allows us to track temperature changes. And what makes a calorimeter great is that it is insulated. So this is called a bomb calorimeter because there's a little compartment where they set off a reaction. And it's very well insulated, so very, very little heat, if any, is escaping to the surroundings. This would be called a closed system. So we can assume here that all the energy lost by the reaction is the same as the energy gained by the water. Okay, we're going to use a couple of styrofoam cups, which actually works pretty well, even though it looks really rudimentary, because styrofoam is such a good insulator of heat. It doesn't allow heat to transfer very easily. So you're going to be using this in the lab to track energy changes by measuring temperature changes. Okay, remember that the energy lost by the hot object, in the last example, water, is equal to the energy gained by the cold object. And that's if and only if the transfer occurs in a closed system. So let's say that I want to use calorimetry to figure out what the identity of this metal is. This is a socket, a Craftsman 18mm socket, and I don't really know what it's made of, but we can use calorimetry to figure that out. Remember that negative Q equals positive Q. The heat lost by one object, let's say the metal, for example, is going to be the same as the heat gained by another object, and we're going to use water for that. So I have a cup of water here. You can see it right down here. And if I put this metal in this water, like so, right now this is just room temperature water. Would you expect a temperature change in the metal or the water? They kind of both started at room temperature, right? But regardless of whether there was a small temperature change or not, right now they're definitely the same temperature. The metal is sitting in the water. There's really no way for the metal to be a different temperature than the water. They're in constant contact with each other, and water transfers heat very quickly and very easily because it's such a good conductor of heat. Whatever temperature difference there was initially, it's pretty much gone now. At this point, we can say that the water and metal are at equilibrium, meaning they have the same temperature. Now, let's say that the metal gave off a little bit of heat. So the metal lost a little bit of heat, and the water gained a little bit of heat. We would say that the metal's Q is equal to the water's Q. The heat lost is equal to the heat gained. Now, we know from the last couple of days that Q is equal to MC delta T. So since we can't really measure Q directly, we have to measure temperature changes. So we have to substitute in MC delta T for both of those Q's, okay? Because all of these things we can measure. We can measure mass, we can look up C in a data table, and we can measure delta T pretty easily with a thermometer. This is the exact same equation as this. I've just subbed in MC delta T for Q because it's equal to Q. And I keep that negative sign because remember that this side is losing heat and this side is gaining heat. So this side has to be negative to show that the heat is leaving. Now if you look at this equation, there's 6 different variables, right? There's a lot of different numbers that we're going to be seeing in these problems. So you absolutely have to keep them organized, okay? The more organized you are in your variables, the easier these calculations are going to be. Make it easy on yourself, get yourself organized, okay? Now, we have 2 different masses. Why are there 2 different masses? What do the variables on this side represent? The mass and the specific heat and the delta T But the mass of what? What are we talking about? Well, let's take a step back and look. The heat lost is on this side, right? What is losing heat? We had said that the metal was a little bit warmer than the water initially, so the metal is losing heat. So this is the mass of the metal, the specific heat of the metal, and the change in temperature of the metal, right? Now what's gaining heat? The water is gaining heat. So this has to be the mass of the water, the specific heat of the water, and the delta T of the water, okay? So it's a lot easier, even though it takes a few extra seconds, it's a lot easier if you kind of keep these separate. So write metal on one side and water on the other. And metal's on the left, in this case, only because the metal's losing heat. Whatever's losing heat has to be on the negative side. Maybe that would be a good thing to write down. Whatever is losing heat has to be on the negative side. Put a big star next to that in your notes, because this is going to be a very common mistake that people make. Alright, so we have metal on our left, water on our right, and a nice big line down the middle to keep them separate. So our mass of our metal, our specific heat of our metal, our delta T of our metal, mass of water, specific heat of water, and delta T of water. Now remember when I said that the metal and the water were basically starting at the same temperature? They're basically both room temperature. That's not going to result in a very high temperature change. In order to get an accurate measurement, we want to have a significant temperature change. So in order to do that, we're going to heat up the metal as hot as we can reliably, and get a good measurement of it. And we're going to use room temperature water so that there's a really big difference in temperature between the metal and the water. Okay, that way when we put the metal into the water, the temperature of the water will rise more significantly, and we can actually measure that change in temperature. So how do we heat up the metal in a way that we know that it's temperature? Can you take this piece of metal and just put a thermometer on it? Maybe put it in a Bunsen burner or on a hot plate and then just place a thermometer on it. Does that give you an accurate reading of the temperature of the metal? Not really, because what you're really measuring is the air around the metal, because it's only touching the thermometer in one specific point. It'd be much more reliable if we put the metal, use thermal equilibrium to our advantage. Put the metal in hot water in order to heat it up, okay? So let's get some hot water ready to go and use the hot water to heat up our metal. Okay, so here's my cold water, here's my hot water. I don't know if you can really see it, it's steaming a little bit. And I'm going to use some tongs because I don't really want to burn myself, okay, in this hot water. So we put the metal into the hot water and give it a little bit of time. Water's specific heat capacity is really high, so it retains its heat really well. Metal's specific heat capacity is typically pretty low, so it changes temperature pretty quickly. And so with our piece of metal in our hot water, after a little bit of time, a couple of minutes or so, we can safely assume that these two are in thermal equilibrium with each other. The metal, the initial temperature of our hot metal is the same as the temperature of our water. So how do we measure the temperature of the metal? Well, all you have to do is measure the temperature of the water, which we can do with a thermometer pretty well. Okay. Now, when I go ahead and take that out, I'm going to go ahead and grab it. Let some of the water drip off so that I'm not transferring a lot of water, and put that in my cold water. Now, because the metal started out hot because it was in the hot water, it now is transferring all that energy into my cold water, okay? As it transfers that energy, this cold water's temperature will rise, probably just a few degrees, but it will rise enough that we can measure it. And then we can use that delta T in order to calculate what the specific heat of our metal is, okay? Now this is what you're going to be doing in the lab. You're not going to be using clear glasses or beakers. You're going to be using a calorimeter. But this is a very important point that a lot of people get confused about. You heat up your metal with hot water. You do not heat it up on the hot plate or on a Bunsen burner because there's no way to reliably measure what temperature you're starting at. You have to know the temperature of your metal before you put it in the water, because that's the only way you're going to know what the temperature change is. If you don't know the initial temperature of your metal, there's no way to know how much temperature change there was in the metal, okay? And then you can't do the calculation because you have too many unknowns. This would be another way to kind of summarize what I just described. In order to do a calorimetry experiment, you have to get your metal hot via hot water bath, which is what I just showed you, putting your metal in hot water, which we're going to heat up on the hot plates. When you transfer that to the sample of cold water, the temperature increases. Assuming we have a closed system, all of the metal's energy is transferred to the water until they come to equilibrium. Okay. Once they come to equilibrium, the temperature of both the metal and the water is the same. And so we can use this Q amount of energy lost by the metal is equal to the amount of energy absorbed by the water in order to calculate our MC delta T. Okay, because we can't measure energy directly, but we can measure the mass and the change in temperature. The entire main idea of why this works operates only on two fundamental principles. One is conservation of energy. Energy is never created nor destroyed. It's always transferred. So what we're doing in this experiment is we're trapping all that energy and measuring how much temperature changes as a result of the transfer of energy. The other key principle is specific heat capacity. I'm underlining and bolding specific because that means that each substance has its own specific heat capacity. For example, iron. There's probably a lot of iron in my piece of metal that I have here. Iron always has the same specific heat capacity, and iron's heat capacity is different from all the other different metals. Every metal has its own heat capacity, and so because every metal has its own specific heat capacity, we can actually identify metals based on what their heat capacity is. If you're confused on any of this, make sure you write your questions down or put a star next to something that you're a little fuzzy on, and then make sure you bring that up in class so that you can get that cleared up. All right, this is Mr. Yergler signing out.